Hello and welcome to the channel Understanding.Concepts.Of.Physics. Today we are going to do three small topics as you can see on the screen. One is the dependency of total energy on simple harmonic motion. The second is conservation of energy in SHM, and the third is the graph of kinetic potential and total energy versus the displacement. So let's just quickly start for learning these things. So dependency of total energy in simple harmonic motion, if I want to find out on what factors does total energy depends, then we are going to use the equation for total energy in SHM. So this thing we have derived in one of the previous videos. Total energy is equal to half of Ka square. Now today we are going to use that same equation, half of Ka square. Now wherever there is a K, I can write as m omega square A square, and because omega is equal to 2 pi f, so wherever there is an omega I can write as 2 pi f. So K is written as m omega square and omega is written as 2 pi f. So I have omega is equal to 2 pi f. Squaring that will give me 2 ka square is 4, pi square as it is, and f square is f square. So in the next equation what we are going to do is we are going to remove these constants, all constants. So half is a constant, 4 is a constant, pi square is a constant. So we come to the equation that energy depends on three factors, that is mass, frequency and amplitude. But there are some technicalities here, that first of all energy depends directly, all of them are in the numerator. Secondly, it's based on the power of 1 for mass, and it is square of frequency and square of amplitude. So finally we conclude here, total energy depends directly on mass, square of frequency and square of amplitude. So if mass doubles, energy doubles, but if frequency doubles, energy becomes 4 times. If amplitude triples, let's say amplitude triples, then energy becomes 9 times because it depends on the square. The next topic today is conservation of energy in simple harmonic motion. So it's a very simple article. You are supposed to do two things. One is for mean position and the other is for the extreme position. So for the mean position we know that x is equal to 0. So for conservation of energy in simple harmonic motion at mean position, x is equal to 0. So now here I am going to use the equation for kinetic energy which I have derived in our previous video. So kinetic energy is half of Ka square minus x square. So because it's a mean position, in place of x I'll put a 0. So this is a 0 square. 0 square is 0, so we just ignore this, and what remains is half of Ka square. So half of K square. And potential energy formula is half of Kx square. So x ke jagah pe you have 0. So 0 square is 0. 0 into anything is 0. So everything goes to 0 and you get a 0. So at mean position you will find out that the kinetic energy is half of K square and potential energy is 0. Total energy is half of K square. This is the formula which we have derived in the previous video. But if you see, there is no dependency on x. So either it is x is equal to 0 or x is equal to anything, total energy will not change. Half of Ka square will remain half of Ka square. Now if you see, this is equal to actually this half of K square, the right hand side is equal. So I can say total energy is equal to kinetic energy. But when the x is 0, when we are at the mean position. So to conclude, at mean position total energy is equal to kinetic and potential is equal to 0. This is our conclusion. And the similar lines we'll do for the extreme position. The difference is only that when you are at the extreme position, x ka value is plus or minus a. So wherever there is an x, I can write as plus or minus a. The formula remains same, half of Ka square minus x square. So wherever there is an x ki jagah pe we have plus minus a, the whole square. So plus a ka square is a square, minus a ka square is also a square, but this a square minus a square will get cut. So you get a 0 over here, and 0 into anything is 0, so you get kinetic energy at 0 at the extreme position. Now if you put the x ka value as plus minus a over here, so it will look like this, plus minus a the whole square, you get half of Ka square. So potential energy comes out to be half K square. Total energy ka formula is half of Ka square, which does not depend on position. So if you see, half K square, right hand side is equal, so left hand side will also be equal. So potential energy is equal to total energy, but at extreme position. So what is the conclusion? So at extreme position we can say the total energy is potential. So every energy at the extreme position is potential, and the kinetic energy goes to 0. And the third and the last part of this video, where we are going to understand the graphs of kinetic, potential and total energy versus displacement. So initially I'll just erase the graphs, and we'll see how it works. So let's say I'm erasing this graph and I'm just moving this thing on the other side. I'll move this on the other side. Okay, so now if I want to plot the graph, I'll just move this somewhere around here. Okay. So just watch what I'm trying to explain this to you. My x-axis is my displacement axis, and the displacement could be plus a and could be minus a as well. Okay, so I've just not written plus over here, so I'll write plus a or minus a, plus a or minus a. Okay, now, and my y-axis is my energy axis. So if you can see, I have plotted energy, and the maximum energy is half of k square, that is the total energy. Then let's plot kinetic energy first. So if I plot a kinetic energy graph, so my first point would be at mean position. If you see at mean position, this kinetic energy is half of k square. So my first point comes out here as at mean position. This is my mean position, this is my extreme position, this is my positive extreme. The kinetic energy is 0. However, if you see the extreme position ka kinetic energy, that comes out to be half of ka square. So this is that point. Okay, so because at extreme position the kinetic energy is half k square, so I get a graph of a half k square. So this is one, and even if it is a negative extreme, the kinetic energy is no, I'm going wrong somewhere here. Now what I was saying is, okay, when you are at the mean position, your kinetic energy is half of k square. So when you are at the mean position, the kinetic energy is half k square, and when you are at the extreme position, the kinetic energy is 0. So this is kinetic energy 0, kinetic energy 0. So if you plot a points, I would get somewhat like this. The first point is here, second point is here, and third point is here. So if I plot a graph, I would get somewhat like this, correct? Oh, I just missed it by some chance. I'll just move it. Okay, so this becomes my kinetic energy graph. Okay, now comes the potential energy graph. Now the potential energy graph is like, at the mean position the potential energy is minimum, so I'll draw that by green, no, maybe white, and the first point is somewhere around here because the potential energy is 0, and the potential energy is maximum at the extreme position. So I have this two points at the corners. Okay, if you can see this point 2 and this third. So I'll join the graph by a curve, so it would look something like this. Okay, again it missed by some points, so I'll just extrapolate that. So I got this as a potential energy graph. Okay, now we come to the total energy. Now total energy, irrespective of what your displacement is, the total energy won't change. So the total energy is drawn by, let's say, green. So this is my first point. Even at extreme position it is half k square, at the positive extreme it is half k square, and at the mean position is also half k square. So I'll just join the line with a very straight line, and I would get something like this. Yeah, this is my total energy graph. Okay, so I'll just move this so that we can just name them. So if you see, it matches perfectly. So this is green line is total energy graph, white line is potential energy graph, and kinetic energy is the orange line graph. So this is all about 3 articles today we have done. I have summarized this in this particular shape in this screen. You can just take a screenshot as well. That dependency is on mass, frequency and amplitude, square of u and power of 1 of mass, and kinetic energy, where it is 0, where it is maximum, how much it is, and the graph looks something like this. So if you are still with me, subscribe the channel in case you have not done so, and keep watching the video from the playlist. All the videos are there in the playlist. You can just watch one by one. It's a connectivity, and more videos are going to follow in the coming days. Exams are coming near, and you can just keep on following to keep on doing one article at a time. Thank you so much. Have a nice day.